Hey guys, I have another example for us. In the last video, I showed how you could derive the general formula for the work energy theorem in one dimension, and how the formula for work was in 1D was the integral of force from x initial to x final. So it's the integral of force along the path. And if the force and the path are aligned, you get positive work. If they're anti-aligned, you get negative work. Because if the two are aligned, then the force tends to make you want to speed up. That's a positive work. It's giving the system energy. On the other hand, if they are anti-aligned, it tends to make things slow down, and that's a negative work. So I have here a situation. I have a cart. I'm imagining the cart starts maybe with some velocity, maybe rest, doesn't matter, and it's going to go down the hill. We know what's going to happen. In the absence of friction and anything like that, it's going to speed up as it goes downhill. So the work due to gravity should be positive in the system. Sorry, I'm making the cart my system. I should have spelled that out. But the work being done by gravity on the cart is positive because the cart is going to speed up and gain kinetic energy. So let's see how that works out, and we will also arrive at, I guess, an even more suggestive formula for work than force times distance. This turns out to be a high school type problem because the force of gravity is constant, and so you can get away without actually using the calculus definition. But I emphasize this is the proper way to define work. It should be an integral over distance, not just multiplying things. All right, so I'm going to make the cart my system here, and I'm going to evaluate the work energy theorem. I can go ahead and give you some numbers. I tell you what, I'll give you some numbers at the end. Let's work it out symbolically, because the form that I want you to arrive at for the work due to gravity is symbolic in character. I want you to remember the form of it, and then we can give numbers if you want. It doesn't really matter at that point. All right, so the system equals the energy, or equals the cart. So the system equals the cart. And after defining my system, the first step when using a conservation law is to write down the conservation law. So that says, in this case, the only sort of energy involved in the system is kinetic energy. So I'm going to say the change in kinetic energy equals the work on the cart, on the system. That's okay. And then I can spell it out. So I could write that as 1/2 the mass times the change in velocity squared, because the mass and half are always constant, so they just pull out. That must equal the work on the cart. So to do that, we have to integrate along the path, okay, along the motion, the 1D motion along the track, the force along the track times the distance, or the displacement along the track from x initial to x final. So as before, we want to solve this so that the motion is simple, so that we only have to consider one coordinate. I'll call that x. All right, so this is a situation where the force along the track, well, let's just review. We haven't done a free body diagram in a while, so let's go ahead and do that. My free body diagram looks like this. I have a cart, I have a weight, and I have a normal force, And I can break the weight into components parallel and perpendicular. As we discussed earlier in the semester, the top angle is theta, which means down here I have the weight parallel, and the formula for that is, given my choice of x and y, minus mg sine theta. And the force perpendicular would be, from the weight, would be minus mg cosine of theta. All right, interesting. Okay, so this is the way I have the triangle here, and this is the way I have the triangle here. Some comments. Notice the force parallel to the track, that would be in the x direction, is negative, but the work is supposed to be positive because the cart's going to speed up. The reason that's okay is because you're starting at the top of the hill. So the displacement is in the negative x direction. Or from a calculus point of view, you're integrating backwards. The lower limit is bigger than the upper limit. So you get a minus sign from that. And then the force itself is negative. You get a double negative, so the work is positive. The force helps you speed up. Okay, so that's one observation. Another observation is that, I guess I'll change colors here. The track lies parallel to W perpendicular. And if you think about it, the angle to the track is not theta. The angle relative to the track, let me call this angle in blue a phi. Okay? And what I know is that phi equals 90 minus theta, if you just look at it. Phi is the angle the track makes with respect to the vertical. It's up here. This is the phi. Okay, phi is at the top. It's going to come out, right? And I want to emphasize, though, phi is the angle between the track and the vertical, or, more important for us, phi is the angle between the track, the motion, and gravity. Okay, the angle between the weight and the track. That's going to be important here in a minute. All right, so now I'm going to plug in everything I know. Let me erase that for a second here. I'll write it better here. Phi equals 90 minus theta. All right, let's evaluate this integral using my formula for the force along the track, which would be the weight parallel. So that would simply be the integral from x initial to x final. And I would have times minus mg sine of theta times dx, where x runs along the ramp. Now, this is a constant, this is a constant, this is a constant. These constants pull out, and this integral simplifies, and it becomes minus mg sine theta times delta x, the change in displacement. So if you go downhill, it's delta x is negative. If you go uphill, delta x is positive. So if delta x is negative, the overall work is positive, whereas if delta x is positive, so if you go uphill, the overall work is negative because you're slowing down. Now, I can use properties of sines and say that sine of theta is the same as cosine of phi. Take that back. Sine of theta is equal to let's see, cosine. All right, so I would say it's equal to, yeah. So it's going to end up being mg delta x times cosine of phi with a plus sign. You have to go through the different properties to work that out of shifting sines and cosines, but it ends up with a plus sign. That's a very suggestive way to write that. Where else have we seen a cosine? It's in the formula for a dot product. So remember, A dot B equals A magnitude B magnitude cosine of the angle between them. In this case, what we're talking about is mg is the magnitude of the gravitational force, the weight. Delta x is the magnitude of the displacement. And then we get cosine of the angle between them. This is nothing other than weight dotted with delta r, really, change in position. Okay. So that's a convenient way to say it. All right. Another thing you can say, looking at this diagram, I've marked out the different heights. And it turns out, if you think about it, delta x times the cosine of phi is actually the same as the change in height, delta y. So for gravity, there's another way you can write this, which simply says that the work due to gravity equals mg times, it's actually minus mg times delta y, the change in height. Okay, so if you go downhill, delta y is negative, and the work will be positive. So you need an extra minus sign to make that work. So these are all handy formulas that you will have that can be useful when solving gravity problems, which we do a lot of in this class. So that's a convenient way to write that. Let's do an example. We can plug in some numbers and get something in the end. Let's just keep that. I'll just make up some numbers for the mass and velocity. We'll see how it plays out. So, tell you what, on this one, I'm going to give you the initial and final velocities, and we'll figure out what is the change in height. How about that? So we'll say the mass equals 2 kilograms. We'll say V initial equals 1 meter per second. We'll say V final equals 11 meters per second. And let's figure out the corresponding change in height to good approximation. All right. So I would apply the work energy theorem. I'm going to say 1/2 the mass times the change in velocity squared. I should be more careful with my parentheses here, so it's really clear. Change in velocity squared equals the work. And a convenient formula for the work is minus mg delta y. Notice, if I phrase it this way, I don't even have to tell you the angle. It doesn't matter. That's kind of interesting. That's kind of really weird, actually. You would think it's got all these dot products things. How can it not actually care about the angle of the hill? It's kind of interesting. And we'll come back to that when we talk about potential energy. Okay, so I have 1/2 the mass times the change in velocity squared as a quantity equals minus mg times delta y. For this example, I have a mass. In fact, the mass actually cancels out. I don't know why I even gave that to you. It cancels out, and you end up with 1/2 the change in velocity squared. Well, and it's almost like I kind of thought about where I wanted to go. The final velocity squared is going to be 121. Initial velocity squared is 1. So this is 121 minus 1 equals g times delta y. So this is going to be 120 over 2. It's about a 60 divided by g equals delta y. It's pretty close to 6 meters. It'd be a little bit more than 6, but pretty close. All right. And that's an example using the work energy theorem to describe the motion along the cart. The important thing I wanted you to see, though, was that this could also be written as the dot product between the displacement and gravity. So that was the weight dotted with delta x, or delta r, sorry. So you can write the work using a dot product here in this, even though it's a one-dimensional example, the vectors were in 3D and we can kind of algebraically introduce or work it into a form using a dot product.